I'll go through it. Exam 1 corrections due at the start of class on Wednesday. I was laid back about so many things. I'm not laid back about this. This is like my little bristly patch right here. Just getting this shit done the way I asked. Simple requests. So easy to do if you just read that. Please read that announcement. I hate having to write not full credit because didn't do what I asked. Oh, God, that sucks. I'll take off points just because it sucks so much to make me write that. I'll be so displeased with having to do that. There are web works active. There's the current one, I think. Let's see, what was the first one? So do we only have one active right now? It's like the Solids of Revolution one.
It's the volume by discs.
Okay, awesome, cool. So we've got that one, web work active. There'll be a new one that opens today after we talk about a few things, and we'll spend time today working on it. And yeah, pretty good. No exams coming up. Certainly not before break. Becky was asking me about that because she's going to be gone on a day. No exams before break. I don't know when that could possibly even happen. That sounds horrible. So, all good. Anything you'd all like to talk about? Let me open up. Is there any questions on yes?
Can I ask about one of the questions?
Yeah, they'd be great.
5?
Yeah, please.
It's problem 6. It is, do you want me to just tell you the
Please.
question? So
Yeah.
it's y equals e to the negative x squared, and then x equals 0, x equals 1, y equals 0, and you need to find it revolved about the y-axis.
Awesome. Oh, Dave, this is the one you wanted to talk. Great question. I'm so glad. This is one of those ones I wanted to talk about. So, outstanding. Fan-freaking-tastic. So, God, now I'm starting to wonder if this one is in the wrong section, now that I think of it. Let's get our graphs out. So this graph here probably looks like this. So that's y equals e to the negative x squared. Yeah, I think it looks just like that. This is 1 right here. And then we've got x equals 0. And this was the y-axis too, you said, Abraham,
Yes,
right?
on the y-axis.
So x equals 0 is the y-axis. Y equals 0 is the x-axis, and x equals 1 is that little chunk. Oh shit, well.
Because don't we have to rewrite it in terms of y instead of in terms of x?
We do, and that's so terrible that I'm going to take this one off until we talk about a better way to do it. How's that sound? Gabe? Yeah. So number 6 is off the plate for right now. Or yes, number 6. Don't do now. Because we do need a different approach. This was miscategorized from the pool that I gathered from. So glad you both asked about that. You saved everybody a lot of suffering. Was there anything else you wanted to talk about? That's the real hard one, right? Okay. Is everything else going good with those then? You found the rest okay? Awesome. Wonderful. Sorry about that.
It took me a while on one of them because I didn't realize it was written as on the y-axis instead of x.
Oh, yeah. So you had to just do everything kind of sideways?
Yeah.
Okay, this is the one I thought you were asking me about, Gabe.
Oh.
But you got it figured out? Okay, beautiful. Okay, so that's it for the web work, current web work. Okey-doke.
Bless you.
Bless you. This. All right, so we're pretty much keeping with this basic idea, but we're going to push it forward a little bit today. So we are going to look at this. This whole web work here is on method of disks. And that was because we were spinning things around the x-axis to get their volumes, and the resulting little elements that we slice things up into turned into disks. So method of discs, everything looks like this in terms of our slices. For the method of washers, which is what we're gonna have now, today, washers. Kind of the same thing. Very similar to the area between two curves, except that things are gonna get rotated. So let's look at what this is all about. We are gonna, just for the sake of discussion, talk about rotating around the x-axis. So I'm gonna have some region that's described by maybe two curves. I'm gonna make this a little more interesting. So then there's y equals g of x right there. I should have made that different color. Make that different color. That blue. Like so. That's nice. I'm gonna spin that region around the x-axis, and I'm interested in knowing what is the resulting volume. So we're gonna spin around the x-axis, so rotate about the x-axis, a full 360 degrees, and find the resulting volume. So rotate R, I'll put that, be a little more precise. Rotate region R, and find the resulting volume. Well, let's think about this problem in two steps, a lot like we did with the area between two curves. Really, this is just two solids we need to find, and we're going to subtract the two volumes. So think of as two volumes with one subtracted from the other. So what we're going to do is first think about that y equals f of x. So the y equals f of x volume is going to look something like this. Oh wait, let's see. Yeah, so it's not even quite that. Let me break this down a little bit softer. So we've got this intersection point here. Sorry, I'm jumping a little bit. So there's an A and there's a B. So let's just put a little star here. First find the intersections, if they're not given to us, A and B. And that's going to give us where to integrate from. And we're going to think about little slices inside here. But we can think of this, like I said, as two different processes. The first one is, here's y equals f of x. I've got this full slice that runs down to the x-axis. So imagine that thing continued all the way down to the x-axis. It would look something like this. Here's A, here's B. And if I spin that, then I'm going to get this outer volume. So, Godspeed on drawing these things out. So this is like the outer volume. And this is all solid, so this thing looks like some kind of little cork or something like that, soft round edge cork that we've got here. And then this inner volume is governed by g of x. And that thing's going to look like this from A to B. Something like that. There's A, there's B. And we're taking those slices and spinning those around the y-axis. And what we get is something that looks like this. And I'm going to pull that out of this. So I've got this new volume here. Let's call this V outer and call this V inner. And I'm going to subtract this one from that. So I'm basically kind of drilling this thing out in this exact shape here. So that our volume of interest, our volume, equals volume outer minus volume inner. Now this is going to get pretty fancy today. We're going to have a lot of practice with this because drawing these pictures and understanding this outer versus inner is going to be really important. So this is all just around the x-axis. We're going to expand it to other axes in just a minute here. But for this one, so our volume formula and this is just around the x-axis, is equal to pi times integral from a to b of outer curve squared minus inner curve squared. Dx or dy, if you're doing like you have to do, sometimes we turn it sideways and just do the whole thing with slices like this, just change it to dy if you need to do that. But this outer curve and inner curve, I don't want to put top and bottom because it's going to change in just a minute. I don't want that to be the way we think of this. Outer and inner is the way you want your mind wrapped around this. So let's do a quick example. Rotate the region bounded by y equals x cubed and y equals cube root of x about the x-axis, and then find the resulting volume. First thing, get a sketch. Definitely essential for these problems. Get Desmos out. You're not good at sketching? Crank out Desmos and have it help you. Y equals x cubed. I hope you kind of know that that looks like that. And then, you know, there's this branch over here. And y equals cube root of x is actually its inverse. So it's just this one flipped over y equals x. And actually they kind of go like this. So we've got an interesting problem here. We'll call this whole thing R. R is composed of two regions. Let's do some deeper thinking. What could you say about those two regions, R here and R here, in terms of comparison? Yeah.
Same area.
Same area. Does that make sense? Do you see that? That these are the same region. So if I want the full volume, I can just do one of these and double it. So whenever you can, exploit the geometry, exploit the symmetry of the situation to make your life easier. So we have each region is identical. So we'll just find one of these and double it. So our volume, and I'm going to write the formula out. Volume is going to be pi integral from, where do you think these intersect as well? 0 for sure. And 1, yeah. You could figure that out pretty easily if you wanted. You could do that by looking at the graphs. You could literally do it by just noting that when x is 1, y is 1 in both these equations. So that checks easily. So hold on, let's back out here. So volume equals, put a little 2 times out in front because we're going to double it. And we're going to go from 0 to 1. Here, my outer curve, you got to be super careful, is this cube root of x. That's the outer one here. So I'm going to have x to the 1/3 squared. Again, this is outer squared minus inner squared, which is now the cube root of x squared dx. And then we could crank that out, but that's not what we're going to do today. We're not integrating today. We're going to set things up today. Because we could do that. This is not bad. That actually, you'd be really happy to get that integral, right? That's like cake, it's like power rule shit. Oh man, multiply by 2 pi, life is good. Let's make things a little more interesting. So that's anytime you have an x-axis rotation. This formula will work for washers or discs. A disc just means the inner curve is the x-axis. Think about that. So this formula is a more generic version. If your inner curve is just this line here, it's just a washer. Got no holes in it at all. But we are going to move away from the x-axis. So let's talk about this now. By the way, could someone do me a favor and send me just like an email that says WebWork 6 on it? Title, remove WebWork 6. Thank you, Sophie. Sophie's doing it, thank you. So I'm taking problem 6 off. If I don't remember who wasn't here when I said that, but I'm stripping that off for now. So new problem. Let's take the region that's going to be bounded by y equals x squared, y equals 0, and x equals, bless you, I don't know what happened with the tree. Maybe I'll bless this. X equals 1. Here's my region. Pretty simple. Y equals 0 is the x-axis, x equals 1. There's good old R. We're going to spin this sucker around different things that we have so far. So, actually, just really quick, what is the volume? So find the volume and just set it up, and I'm going to ask you to do this. Find the volume if we rotate around. Can you just do this one for me? Just set up the x-axis volume just to make sure you're like moving your hands and you're thinking about what we're doing here. What is that volume formula? Super bored, you could probably crank it out in seconds after you get the formula all worked out. That's a beautiful answer. That contains all the right information, and gosh, I just have to do it because it's so easy. I just want to do it. It's just pi over 5 units cubed. Neat. Very simple. Let's do something a little more interesting. Let's rotate this around the line y equals -1 now. So now I'm doing something a little different here. We're moving away from the x-axis. Now I'm going to spin around the y-axis. So this one here, let me sketch out. What did this one look like? So this looked something like this. Looked like a very sharp, cuspy tack kind of thing here. Those lines aren't quite right there. Yeah, I don't know. That's kind of shitty. There's the line. There's the rotational axis. So that's this one. The second one I'm going to say is rotate about y equals -1. So let's think, can you like picture that thing in your head? What is the shape going to look like? Take a moment, just do that. Maybe try to draw it. That's always a whole different challenge than visualizing it.
When you rotate it, does it move or does it stretch?
Ooh, can you explain what you're asking? That's an interesting question.
Since when you rotate around the x-axis, it just like flips down.
Yes.
Since you're rotating around an axis that isn't just 0 and the object intersects at 0, does it have to move to rotate around that axis?
Yes. So imagine, you know those little party decorations you get, and they're like made out of tissue paper, and they come all folded up like this, and you pull them, and you go, and you kind of pull them apart, and they turn into a full thing, and it's all like kind of got little diamonds in the side connecting. Does everybody know what I'm talking about?
I think so, yeah.
No, I don't know what the hell else to call them.
Spheres.
What's that?
The spheres?
Oh, they could be spheres. I've seen them like for like St. Patrick's Day and shit. How about this? A fan. Just imagine a fan. You open up a fan and just spread it out like that. That's not quite as good of a thing. So Sophie, I guess what I'm trying to say is that I'm going to take this shape and imagine it, okay, Imagine this is the shape of my phone. Here's my axis of rotation. If this was a square, what would be happening is I'm just moving it around like this. So imagine this shape, just, imagine my phone was that shape, moving around that axis in a full 360. I don't know if that helps, Sophie?
Mm-hmm.
Okay. So when I do that, what it looks like is kind of a washer. It's gonna look like this. You're gonna have this sharp front edge. You're gonna have this outer flange on it, but the inside is gonna be straight. It's gonna have a straight inner edge, and it's just gonna have a circle kind of right there. Something like that is gonna be the shape. The rotational axis is right in the center, but this thing is hollow. It's kind of like, there's almost like a cylinder removed from the center of it. Does that help? Yeah, good. See where I'm going? Yeah. This is like the hardest part of all this, generally, trying to just get your mind wrapped around what these things look like. So let's think about what's happening here. I've got this basic element in here, one of my basic elements for integration like this, and I'm going to spin that around. Well, what I'm going to end up with is little elements that are just washers. Let's go here. There we go. So each little slice is going to look like this, and you have to think, what is the volume of that thing? It's just the formula we were using. It's just the outer minus inner. We just have to tweak our mindset just a little bit. So think about what's outer here. Wow, right back to me. Outer is from the axis of rotation to that top curve. So that's my outer radius. This is my inner radius, this piece here. So that's going to be the inner radius. So what I'm going to think about now is this formula. So our volume is going to be pi integral from start to end, outer radius. I'm going to call it outer radius because it's not exactly the curve, it's a little tweak. Outer radius squared minus inner radius squared, dx. So in other words, I'm finding the volume as if this thing were totally solid. So the first thing is, this one here, if I didn't have this, I would be finding this volume here, but it would be a solid thing. It would just be this like a little platform for like a circus or something. So some poor fucking elephant would have to stand on that or something. This is sad, it's heartbreaking. So what we're gonna do is, we're gonna take that and then we're just gonna remove this cylinder in the middle. And the cylinder is this piece right here that gets spun. We're gonna take that out. That's this piece right here. So for this one, my volume integral is gonna be pi equals, or excuse me, volume equals pi, integral from start to finish. Well, I gave you the start, well, it's kind of, I didn't quite, but it's right here at 0. Finish is at 1. Outer radius, what's my outer radius? Somebody tell me.
X squared plus 1.
Beautiful, yeah, absolutely. It's this distance here, which is 1, plus this distance here, which is x squared. That was Dwayne, you say that? Yeah? Yeah. So it's this 1, this constant 1, plus the x squared that's going to change as the x slice moves. So this is going to be 1 plus x squared, squared. This is my outer radius. Now here, how can you possibly think about that? Well, here's a good way to think about it. Maybe your mind isn't working like that. What you can always do here is do top curve minus bottom. And that's going to equal your outer radius. Oh, excuse me, top curve minus axis. This is your outer radius. So how do we get that? Top curve here is x squared the radius, or the axis is -1. So I'm subtracting off -1, that's x squared plus 1. So that's another way to think about how to get that outer radius. I'm going to subtract off the inner radius. What is the inner radius? 1. Permanently 1, right? Notice that the inner radius, which is, let's get it here, is going to be the bottom curve, bottom of region. Take this off, like here, this is just for here, this works, because it's gonna change if the axis was on top. So for here, we need to do a bunch of these and then they'll all come together, I promise you. Bottom of region minus axis. So that's gonna be 0 is the bottom of my region, it's always 0, the y coordinate, minus -1. So this is 1 squared. Dx. And then I find that integral, and that gives me the volume. We're going to do a bunch of these so that this makes sense. Let's move the axis above it now and see how that changes things. And you'll see why I'm calling things outer radius and inner radius. I think so. I hope so. So here's my region again. This is x squared. This is 1. That's the beast. I'm going to spin it around y equals 2. So now, spin around y equals 2. You got to draw these pictures out so you can understand what's outer and what's inner. So let's do this together. So v is going to be pi integral from start to finish. Start is 0, end is 1. I'm thinking of vertical slices. Where do those slices run? From 0 to 1. The outer radius, let's just do this. Outer squared minus inner squared dx. So that's going to be pi integral 0 to 1. Always do top minus bottom. So look, what is the top curve? Top curve is y equals 2. That's the top now. The bottom is, let's see, what am I doing here? The outer. This is the outer edge now. Do you see that? This will be the outer part. So it's going to be 2 minus 0. So the outer curve is always 2 squared. Or the outer curve is 2. The distance, outer distance, let's put that here. Inner distance. This is a constant 2 here, because that's this all the time. What's my inner distance going to be? Somebody besides Voin. I know Voin's going to answer this in a second if I don't say that.
X
So
squared minus 2.
say that again.
X squared minus 2.
X squared minus 2. So let's check that out. So if I do x squared minus 2, you're definitely on the right track, Scotty. The problem is here, x squared is underneath this guy here. So I'm going to do it just the other way. I'm going to take 2 minus x squared just to keep that thing positive. But we're going to square it, so it won't matter. But let's just get used to thinking about that top minus bottom here. So here I'm going to do 2 minus x squared, and that gives me this distance right here. See, I'm taking the full distance minus that little bitty x squared, but you have yours would have worked out great. There's my volume integral, done. We're not going to crank it out. Let me see if there's any questions before I erase anything, and then try a few. Yeah, okay.
Why couldn't you just like subtract or like use x squared instead of 2 minus x squared? Like just subtract that volume from the bigger volume.
So what is the bigger volume here? So let's think about that. The bigger volume is going to be this giant cylinder, right? If I spin around this thing and this flat edge is my outer one, that's going to be my outer volume. My inner volume is going to be this weird little shape, this thing, this region here spun around. So I can't just subtract this piece off because this piece, when we did it before, that was spun around this way. So now we're spinning around a whole different way. And we literally have to subtract off, we want this piece left. So what's left is the weird little, like when I subtract out the middle, got that in there, right? And they kind of like meet in the middle, and then there's like a hole somewhere inside there.
Okay.
Does that picture help
Yeah,
a
yeah,
little
yeah,
bit?
I got it.
Okay, cool. Sophie?
I guess I'm just confused as to when you're taking the inner, is that little sliver only x squared, or is x squared the whole line?
X squared is the whole line. So for any particular x slice that I'm at, this height right here, this distance from the outer edge to this inner thing is gonna just be x squared.
Okay.
So for each slice, I'm gonna take the full thing, which is 2, minus this little slice, which is x squared for each x chord.
And that's the case for any point in that graph? It'll always be x squared?
Yes. Yeah, so like if I'm here, let's say I'm at 3/4. What is this distance right here? It's going to be the full distance 2 minus this distance, which is 3/4 squared.
Oh, I understand. So if
Does
you're
that
doing
make
it at 1,
sense?
if you're doing it at 1, then it's just x squared.
Yeah.
Okay, that makes
Yeah.
sense. Got it. So if you were at 0, you just wouldn't subtract anything.
Correct. Yeah, it's 0. Yeah, it's 0. It's just 2, and you subtract off 0.
Okay.
Yeah.
Cool.
Yeah, good stuff. Other questions on this? All right, let me give you a couple. Let's try it. So, on the next exam, which will be after the break, I'm gonna give you a little collection of regions and places to rotate them, and we're gonna knock them out. So let's just do one together here, just to make sure everybody's on the right page. So, given the region, ooh, let's do the one we already did, bounded by, this will be fun. Y equals x cubed, and y equals cube root of x. Let's go back to that, because we already understand that region. That looks like this. And this is 1, right here. Let's spin that. Find the volume if we rotate about, and just set up the integral, don't crank out the value of the integral. So let's just do a few things here. First off, just see if you get this, remember this one. The x-axis, B, let's do the line y equals 1, and then let's do the line y equals -2. Let's set up those 3 volume integrals, see if we got this. I would definitely draw the axis in there, visualize who's outside and who's inside. It's always outside minus inside. If you get a negative value for this, you probably subtract it backwards. Yeah.
Are we only doing for x equals 0?
Yes, sir. Yeah. So, yes. So this region started at 0. Yeah. So just 0 to 1 are your slices. I'm glad we did this one. It does have a little bit of different stuff. Just a little. So all really different looking formulas. I'm gonna come around, see how everybody's doing. Yeah, that's great, that's great. No. I mean, the answer will be the same, but the integrals won't look the same. Yeah, you're right, you're absolutely right, yeah. Numerically, they'll be, Voight was just pointing out like a really cool observation that these two would have the same value. They won't look the same, but if you crank them out, like imagine the shape that came out, like this little piece here, that little tack, and then this was gonna look exactly the same, so there's a symmetry there that means these would give the same value, just, wow, I'd rather do this one. Abraham? Yes.
Shouldn't it be 2 pi?
For which?
Because I think you mentioned for the x one it was 2 pi and then the integral.
Oh, I changed the region up. It was, if we had that other little piece out here, that was when, yeah, so good, great observation. Yeah, we're just gonna do, I'll add a few things here to keep this one in line. Also, y equals 0 and x equals 0, so we'll cut it. Great call. Doing good, Jaden?
Yeah, long day.
Yeah, long day already. Oh, man. At least you get to end it, well, you probably don't end it for a
No, I
long
have a
time.
Physics exam after this.
Oh, shit.
Yeah.
We're gonna wrap it up here after this, so you can do as you see fit. Probably should go get some food or something. Would anyone like me to go through any of these? I think they're all right. So this is like different, right? It's like we're doing calculus, but we're doing this meta analysis. We're setting up the calculus.
So it will usually be if it's rotated by something above it, you're gonna subtract from it, and then the otherwise you're just adding it.
Absolutely. The reason it looks like adding is because these have been negative lines. Let me if I had something like this, just really quick, if this region had been up here and I was rotating around y equals +1,
You just subtract 1.
then there
Yeah.
would be a subtraction, yeah. So I think the plus is coming because of the negativeness of those axes. Yeah, great question, yes.
And we're just assuming in this case, since you gave x equals 0 and y equals 0, but if you had given a different case, then like, for example, if you had given like, I don't know, x equals 1,
For this problem here,
yeah, in
Yeah.
that case, like for the last one when you're rotating around y equals -2, how would that change?
so I don't think I'm understanding exactly how you're changing the problem.
I guess I'm just curious, like if you change the points that you're trying to find the region within, since we have nice numbers there and it's only 0 and 1,
Oh,
like kind of how you were explaining in the last one with how like if you had it as x equals 3/4, then it would be 3/4 x squared.
yes.
As part of I'm just curious like as to how that alters.
I I'm still, it's like when you say changing the numbers, do you mean like the range? of-
Yes.
Oh, okay. That's just gonna change this.
Okay.
So like even, yeah, we'd have to be careful. Yeah, that would just change these numbers though, I
Okay.
think. The key thing, Sophie, is to imagine the slices and like where the slices run from to.
Okay.
That's the key thing.
Okay.
Okay, cool. So that's all I got to tell you. It's enough. There's like a new collection of problems involving this in the web work. Let's do that. Let's get on these. Let's work on them. We'll probably work on them some on Wednesday after I tell you one new thing, of course. A little bit of info each day. So maybe finish up that first one while we're together and then move on. I'll run to the restroom really quick. We're right back. It's telling you that it just stops at the x-axis, I guess. So it's just letting you know that you're not really passing. Yep, it's just that little region. Yeah, but FOIL it out, use exponent properties to simplify the e to this, because you're gonna get e to the 2x times u, and 2x bringing that is 1, and then it'll just be easy. Yeah.
Thank you.
Let me stop. Oh, gosh. These are some interesting numbers, okay.
A little bit conservative.
Yeah, so that's. Where'd that? Oh, that was after integration. Okay, got it, okay.
Did I foil this?
Yes, yes, no, no, you didn't. What's your outer term? The first and the last are great, but your outer and inner,
Oh, it's 10x.
there you go. So you can probably take that and propagate it through it.
Oh, okay.
That's your problem.
I don't know where I got the 2. I think.
Well, kind of, I
think
mean, I
just
kind
added-
of know why.
I think I just added that.
Yeah, I think so, yeah, or if it's been 1 instead of 5, that would have. Good, all right. Okay, gosh, okay, let's take a look, so this one is on the y-axis. Is this your? Yeah, I'm just curious how you got, I'm not seeing 4x plus 32 anymore. How'd you get this? Where'd this come from? Okay, so, yeah, let's just see real quick, so that's a line, right? As you all know. So that is a line of slope 4 through 32 on the axis here. So it looks like that. So that's y equals 4x plus 32. So this is your outer, like your radius is that whole distance there, because we're going around the x-axis. So I don't, about the y, oh, this one's about the y-axis. Son of a gun, I don't want that in there. Which problem is this? This is on that other previous. It shouldn't be, but it's gonna be a pain in the ass, kind of. We could do it the smart way by actually just doing this little region right here, taking it off the bigger volume that we're gonna get. But otherwise, you actually have to break this into 2 parts. If we're doing around the y-axis, so let's take a look here. Second that. And that. And we're going around this way, right? So our elements are gonna look like this. Notice we're gonna have a change in top and bottom right there. So you kind of need to do 2 different volumes. The first one is from here to here, and the second one is from here to here. And I guess you got this by like solving backwards, kind of, or something.
I'm just trying to find.
Oh, you just forgot to do that before. That's what I'm missing here. Oh, got it, man. Okay, I'm with you. Okay. So this is just a portion. What you did was you did, actually, okay. So let's talk about what's going on. When we spin this thing around, we're only doing here to here. Oh, well, wait, what are we doing? No, I'm doing it all backwards. I didn't even look at my region. Sorry. So we have x equals 0, y equals 0. It's this. That's the region. Okay. So now I see why you're going to 32. Okay, I'm with you. It took me a while to get with you here. But we're still gonna have, yeah, okay, boy, you just like moving way faster than I did there. So let's see, so it's gonna be pi times integral from 0 to 32, I agree. And my outer, it's gonna be 0, I guess it won't matter because I'm squaring it, and then we get 1/4 pi 5/4 should be squared. That's your problem. Okay. Good work though, really good work. Yes, Gabe.
You know, number one is also like revolving around the y-axis.
Is this on the new one?
Yeah.
Okay.
Should we?
Okay, that one's not too bad. Let me show you how to do
Okay,
that.
cool.
So when they are around the y-axis, you do what we're doing, but you change your perspective. Sorry, thanks. So Gabe is looking at, which one is that, Gabe, 5?
Number one.
Oh, number 1.
Yeah.
Okay. I just really jumped right in there. All right. So, what are the curves you're given there?
Y squared and 4y plus 5.
So y squared equals x.
Yeah, yeah. Sorry.
Okay, that's okay. And then, sorry, what was the other one?
4y plus 5 equals x.
Okay. So these are viewing things sideways. Instead of this being y equals x squared, we're treating this like it's our y-axis here. So when I sketch out that one, you can get Desmos out to check them out, like that. And then this one here, let's see, when y is negative 5/4, x equals 0. And when y is 0, x equals 5. Yeah, so we'll say like right here. So I'm going to exaggerate this. Let's say that's x equals 5, because otherwise it's going to be really weird. So is this what your region's looking like, Gabe? Like this little like bow?
Yeah, yeah, yeah.
Okay. Cool. So step 1 is find these intersections here and here.
Mhm.
And have you found those yet?
I just set the two equations equal to each other, and
Perfect.
I got negative 5 and 1.
Yeah, that actually sounds perfect.
Or positive 1, sorry.
Yeah, okay, that sounds. Right. Yeah, so like, my pictures, wait, let's double check that, hold on. Let's
I
see
think
this.
you might have to flip the coordinates.
I think so. Yeah, I think you got your signs backwards. No, you did. Yes, you did. Because this
Okay.
is, so this is your factorization?
Oh yeah, I did get
Right,
percentage.
yeah, you got it a little backwards. Because looking at this picture, I was like,
Mhm.
that doesn't make sense with the picture.
Yeah.
But this does, that we would be going from negative 1 down here to 5 up there.
Yep.
Yeah, and then we do our slices like this. And so we're gonna do pi integral -1 to 5. Abraham, what was it you were saying? So I didn't mean to like just dismiss what you were saying.
Oh, no, it was just flipping them.
Oh, okay, yeah. And then I'm gonna do, let's see, so we're spinning around that way. So my outer radius for this particular y slice is going to be, is just this outer curve, 4y plus 5. So I've got 4y plus 5, and that's this distance here. And then I'm subtracting off this inner distance, which is the y squared dy. So I think this should get us.
Oh, okay.
Does that make sense?
That does make sense,
Okay.
yeah. Thank you.
You're welcome. Yeah, Daniel.
So this one this also has to be go around the y-axis. And probably just looks like a cone, and just use the volume of the cone.
yeah, sure. If you know, what is it, like 1/3 pi r squared h?
Something like that.
Yeah. Let me talk about that one though. Yeah. Which one is that, Daniel?
4.
It's number 4. Could you give me those equations, please?
Y equals 4x plus 28, and y and x both equal 0. Y equals 0,
Oh,
x equals 0.
got it, got it. So for number 4, you're gonna have a rotation about the y-axis. You're gonna have to change your perspective as well here. 4x plus 28 is got a y-intercept of 28. This one's really counterintuitive because this is the region you're spinning here. And we need to get that intercept. Well, we don't need that intercept at all because we're doing slices like this because we're spinning around the y-axis. So you do need to solve that top equation. And Daniel's question was, this is going to look like a cone. Can I just do the volume of a cone? Yeah, you can. But I would just make sure you could cooperate, doing it the other way. So you do need to solve that for x because you need to know this height here. So x equals y minus 28 over 4. So that is your outer radius. Your integral will take place with respect to dy. Yes.
Okay, so I just square that.
Yeah, basically, yeah, just square that and you're good to go.
Okay.
Yeah. And I guess 0 to 28 is gonna be your bounds of integration. Yeah. It might be cool to check out the formula, and just see.
Yeah.
Ooh, I'm gonna derive it. I'm just gonna go ahead and derive the formula. Let's do it. Let's see. So if I had a cone, look like this. I'll say has bottom radius r and height h. That would look like this. This would be h, and this would be r. Now spin it around the x-axis. Gotta get the equation there, so that's y equals, what's the slope there? Negative r over h x plus r. Oh, this is cake. So pi integral 0 to h. So cool. Yeah, that's the formula. There you go. It is. It's pi over 3 r squared h. Proven.
That's pretty cool.
Isn't that fun? Yeah. Thanks for giving me something fun to do. That's awesome.
So, one problem one here.
All right.
Let's see. Let me change those. Maybe I'll do something else later.
Okay, so we got x equals y squared. So your curve, your picture's a little off. So
Yeah, I know.
Oh,
it's
you
supposed
know
to-
that.
I realized
Gotcha.
after the fact
Gotcha.
that it's supposed
Okay.
to be something
Cool.
like this,
Cool.
yeah.
Cool. Can I redraw just so I can
Yeah.
think? Because I definitely need to make sure it's the same check. So x equals y squared. So that, and then that is. Oh, that's a lovely one. So let's see, when y is 0, x is 6. And then when x is negative 6, y is 0. Is that right? Yeah, oh wait, when y is negative 6, x is 0, yeah. 6, that. Oh, I guess, oh, it's this, yeah, what you're doing, okay, got it. It's that guy there.
It should be
Let's see, so guys.
or one of them is
Yeah.
negative 4.
Gosh, I don't know, let's just double check, so we can get y squared equals y plus 6. I think actually we're gonna get something out of that, we're gonna get like a 3 and a 2, I think.
That's what I had the first time I said that one was wrong.
So, you and I are setting equal to the one side. So I get negative 2 and positive 3.
Okay.
And that probably could be, that's definitely not helping.
Yeah, cause that's what I had up here
Yeah.
with that.
And what are we doing? We're doing around the y-axis here, so we're gonna do, yeah, okay, otherwise this looks good. This looks good, it's your limits are just off, that's all. Yes, ma'am.
So this one is the question. So it's yes, it's like that.
Yeah. That's what I was just talking to Abraham about.
And I ignore this.
So your limits are not correct, that's the
Okay.
problem. So,
That's what I
here,
was
let's talk about how you got this. So how did you come up with the intersections? Like, what was your?
So I looked on Desmos because
It's okay.
I just started doing it so I can put it back out.
Yeah.
But this is what it gave
Great,
me.
okay. And then you kind of estimated those, or
These numbers?
the 0 and the 6? So
Oh,
the 0 and the 6 is what I'm wondering about, because you're,
I did from here.
okay. But it starts down here.
Yeah.
So, let's talk about how to solve those. You're just gonna set,
Then equal to each other.
so y squared equals y plus 6.
Okay.
And then you're gonna get that all to one side.
Yeah. Factor now.
Factor. So where are my actual intersections?
3.
Yeah, so this is -2, and you kind of got it there, you got like a -2 written there, and then a 3 here. So your slices are gonna run from -2 to 3, that's your problem.
Right, these two.
Yeah,
numbers.
yeah.
Okay.
Other than that, it looks great.
Okay. And then this was the last one.
Oh, okay, cool.
I have to work on the top.
Oh, it's okay, it's
But
okay,
I
yeah.
know, I think I got this.
Yes, uh-huh, good.
So then I did this to get
Was this one a volume or an area?
volume.
So there's no square I'm seeing here, and that's,
Okay.
so let's take a look, so you can go check it out when you get your laptop. So, let's sketch up this region. Is it okay if I do it?
Yeah,
I
that's
guess I
fine.
already started doing it, you know, but,
Whatever works.
okay, cool. So, e to the x plus 3 is gonna kind of go like that. And then, y equals 0, x equals 0, and then x equals 1. So it's gonna be
Okay.
this region here, and I think we're probably going around the x-axis on that one, I hope so.
Yeah.
Okay, good. So, do you see what might be, let's see, what does our volume gonna look like? What's that gonna look like for this?
This square.
Yeah, there you go, that's it, right there. And then just integrate it from 0 to 1. And FOIL it out, you know, and. You're welcome. Okay, so this is looking good. This looks real good. Let's see. Yeah, I love the way that looks. Are you getting them right? right? It looks
Oh,
like you're
yeah.
getting a couple right, yeah.
Yeah, it's.
I was gonna go over that over.
It's very good on this.
Yeah.
Get a bunch done and we can talk on, Wednesday or tomorrow at office, I got office hours tomorrow, 3:30 on Zoom.
Okay.
Let me know if you're coming.
Alright, for sure.
Alright?
Sorry.
Bye, thank you. Bye, thank you. Thanks for the problem.
Yeah, no
Bye.
problem.
Anytime, right? Did they get that one to work out, Abraham?
Not quite, but I was getting there.
Okay.
Just had to solve out the,
Do the painful part.
Yeah. Have a good one. You too, I'll see you Wednesday. Oh, these look great. Yeah, this is great, and then just staple them to the back. We'll be solid. You're welcome. So, I'm just curious, what happened on that exam? Because I was expecting you to like just smoke that thing. Oh, shoot. Really? Dang. Oh, that stinks. You should have let me know that.
Yeah, just a couple of dumb mistakes. You know, cause I don't know what to put for explanations on mine, cause on one of them, when it was the derivative of something, instead of dividing by, so, on this one, instead of, multiplying by this u out here, so instead of multiplying by 2, I divided it. So I had 3/2 cosh. And
Oh,
then on this one,
yeah.
I just took a bad derivative. so-
Just put bad derivatives.
Okay.
You know, like your explanation is brain got fried for a
Yeah,
minute or
yeah.
something. Yeah, yeah. Okay, sounds good. Yeah, you
Have a great day.
You too.